Hello everyone. This video is about the axioms of quantum mechanics. If you want to understand quantum mechanics but you are struggling with wave functions, double slit experiments, entanglement and all those things you find in popular science books, then what you need are the axioms of quantum mechanics. They are the mathematical rules of the game. The good news is that the maths of non-relativistic quantum mechanics is linear algebra, which is not too difficult to understand. The axioms of quantum mechanics are the equivalent of the Newton's laws in classical physics. They are counterintuitive, but you can use them to predict the result of any experiment. And they never failed since they were introduced 100 years ago. These axioms are often associated to the Copenhagen interpretation of quantum mechanics, which is one of many equivalent interpretations. The number of axioms and the way they are stated may be different from textbook to textbook, but all the formulations are equivalent. Axiom 1. The state of a quantum system is an element of an Hilbert space over the complex numbers, normalized to 1. The state is called the wave function. States that differ by a phase are equivalent and represent the same state. The state of a composite system is the tensor product of the states of the components. Let's see what it means. The state of a classical system with n degrees of freedom is an element of a vector space with dimension 2n. I will use the words vector space and linear space with the same meaning. For example, for a pendulum which has 1 degree of freedom, we can describe its state with two numbers. One for position, associated to potential energy, and one for angular velocity, associated to kinetic energy. This is a system with a finite number of degrees of freedom. For a vibrating string, which has an infinite number of degrees of freedom, the state is given by two functions. One for the position and one for the velocity of each point. This is because the equivalent of a vector for an infinite dimension linear space is a function. A 1/2 particle quantum system is a system which angular momentum can have only two values, 1/2 and -1/2. For the classical equivalent we would need four real numbers because we need two numbers for the angles in space, for example azimuth and elevation, and two numbers for the angular rates. In the quantum case the state is an element of an Hilbert space over the complex number, of dimension 2. Which in practical terms it's a vector with two components where each component is a complex number. This state is called the wave function. It is usually denoted by the letter psi and gives only the direction in space. The angular rates are something that do not make sense for this system. To give its state, we need just to describe its orientation in space. It seems that we have too much data for describing a direction in space because a direction can be given with two real numbers while we have here two complex numbers corresponding to four real numbers altogether. One real and one imaginary part for each component. However, we want also the wave function to be normalized to 1, which removes one data, and we said that two states that differ by a phase are equivalent, which make one data redundant. Since the wave function is a vector, we need to choose as basis for the underlying Hilbert space. A common choice is to measure the spin with respect of the z-axis. In this case the basis is given by the two orthogonal vectors spin up and spin down. The two complex numbers of the state are therefore its components with respect to this basis. Any linear combination of states is called a superposition of states, and it is itself a valid state being an element of the Hilbert space. In this basis the up state is the 1, 0 vector and the down state is the 0, 1 vector. Note that the minus up state is orthogonal to the down state. This is because the space of rotations of a spin is different from the space of rotations of a vector. A 1/2 spin particle has to go around twice before it goes back to its original space. In the same way, you can describe any other direction, in spin-rotation space, with two complex numbers. For example, these are the states for the left, right, back and forward directions in the up-down basis. For each direction there are two different orthogonal states. Don't focus too much on how to represent the state in spin space. The important thing here is that the state of a quantum system is a vector with complex components. There is no canonical way to derive the structure of the state of a quantum system from its classical equivalent. It is somehow given in the theory. However, working with states and getting familiar with them, you will see that in general guessing the structure of a quantum system is not difficult. All the rest comes from linear algebra. For example, if you change the basis vectors, the coefficients of all other vectors will change accordingly. These are the representation of some vectors in the up and down basis. And these are the very same vectors representing the states in the right and left basis. You can change the basis of a vector just projecting it on the vectors of the new orthonormal basis, using the scalar product. Try with the example I gave you. I will talk of the scalar product later on in the video. Change of basis is an important concept in quantum mechanics. Note that the notation I have been using is not very common. Common notation for the basis vectors on the z-axis are arrow up and down. Common notation for the basis vectors on the x-axis are plus and minus. I give now an example of a system with an infinite dimension state. The particle moving on a line. The equivalent classic system has state dimension 2. It is described by just two numbers: position and velocity. In the quantum case, the wave function of particles with definite position and unknown momentum are Dirac delta functions centered at the particle position. Any other state can be defined by a continuous complex-valued linear combination of the above states. This is once again a superposition of states and gives the general wave function on the system, which is a complex-valued function. We also want the amplitude of the wave function to be 1. We want to represent the same system in a different basis. We want to use the momentum basis. The wave function of a particles with definite momentum and unknown position, are wave oscillating all the way from -infinity to +infinity with definite wavelength depending on the momentum. This is due to the principle of wave-particle duality. Now, suppose we have a wave function in the position basis. We know from Fourier analysis that we can represent this function as a continuous complex-valued linear combination of waves of definite wavelength. We need also a normalizing factor to keep the amplitude of the function to 1. This continuous linear combination psi of p is the wave function in the momentum basis we were looking for. The change from the position basis to the momentum basis is very similar to a Fourier transformation. In quantum physics, if we know the position state of a particle, we know also its momentum state. This is not true in classical physics. Note that, from Fourier analysis we know that the more the function spreads in the position basis, the more it shrinks in the momentum basis and vice versa. This is another way to state the Schrödinger uncertainty principle. States come in two forms. Ket vector are elements of the Hilbert space. Bra vectors are elements of the dual space. The relation between the two is complex conjugation of each component. They are exactly the same vector corresponding to the same state of the system but in a different form. A practical rule for calculations is to see ket vector as column vector, and to see bra vector as raw vector with all components complex conjugated. You can then apply the rules of matrix multiplication when working with them. Scalar product is legal only between a bra and a ket vector, which in fact gives a scalar. Scalar product can be used to define the module of a state. A product between a ket and a bra gives instead a linear operator. In classical physics, the state of a composite system is the Cartesian product of the states of its components. This means that to get the final state you just put side to side the coefficients of the vectors of the component systems. In quantum mechanics, the state of a composite system is the tensor product of the states of its components. Tensor product mixes the coefficients of the vectors of the component systems. This is an important feature of quantum mechanics that leads eventually to concept of entanglement. Axiom 2. To each observable, it can be associated a self-adjoint Hermitian linear operator acting on the state space, and vice versa. Let's see what it means. For classical systems, the state can be measured and known exactly. For quantum systems, quantities related to the state of the system can be known through experiments. These quantities are called observables. To each observable, it can be associated an Hermitian linear operator acting on the state space, and vice versa. We need to define Hermitian operators. Given an operator A, acting on a space H, and an operator A star, acting on the same space, we say that A star is the self-adjoint of operator A, if the following identity holds. Note that the angle brackets mean scalar product. If A and A star are the same operator, then we say that A is Hermitian self-adjoint, or Hermitian, for short. When working with spaces of finite dimension, operators are matrices. In this case, being Hermitian means that swapping indices of the matrix corresponds to complex conjugation. Hermitian operators for spaces over the complex numbers is the equivalent of symmetric operators for spaces over the real numbers. Why Hermitian operators? Well, this is an axiom and therefore why is not the right question. However, when you get to the end of the video, you will see that the whole thing is consistent. Now, I will say a few words on operators. Linear operators take vectors and transform them in both direction and amplitude. There are special directions where the vectors change in amplitude but not in direction. These vectors are called eigenvectors. And the amount the vector length changes is the corresponding eigenvalue. To distinct eigenvalues, correspond linear independent eigenvectors. And for Hermitian operator, to distinct eigenvalues, correspond orthogonal eigenvectors. This means that if you have an Hermitian operator with distinct eigenvalues, you can use the eigenvectors to construct an orthonormal basis for the underlying space. In this basis, and for finite dimension spaces, the relevant operator has a diagonal matrix representation. A remarkable example comes from Fourier analysis. The wave function in one dimension is simply the eigenvector equation relevant to the second derivative operator, which is a linear operator. Its solutions, waves of any wavelength, are functions that oscillate periodically, and they form an orthonormal basis that can be used to construct any function. Because they are a basis for the underlying space. The Hermitian operators, associated to the spin observable of the 1/2 spin particle, can be constructed from the Pauli matrices. You can easily check that they are all Hermitian matrices. These are the operators associated to the spin on the x, y and z axis. Since the Pauli matrices are a basis for the space of 2 by 2 Hermitian matrices, all other operator associated to the spin in any direction are a linear combination of these ones. The Hermitian operator, associated to the position observable of the particle on a line, is simply the function x. The hat symbol on the x means it has to be seen as an operator and not as a function or a variable. This is a linear operator because it satisfies the two following properties: additivity and homogeneity. The Hermitian operator, associated to the momentum observable of the particle on a line, is minus IH bar times the derivative. This is a linear operator because the derivative is linear. Axiom 3. The outcome of a measurement of an observable is one of the eigenvalues of the associated Hermitian operator, and the probability to have that outcome is the modulo square of the projection of the state on the relevant eigenvector. Let's see what it means. Given a wave function psi, describing the state of a system, and an Hermitian operator A associated to an observable, the outcome of an experiment, to measure the observable A, is a real number, and it can be only one of the eigenvalues of A. Moreover, if the phi I are the eigenvectors of A, we know that they are orthogonal to each other. Then we can always normalize them to 1, such that the phi I are an orthonormal basis. Given the phi I, we can define projection operators pi, which project any vector along phi I. By multiplying pi on the right by a phi ket vector we get the component of phi along phi I. And by multiplying the result on the left by a phi bra vector we get the modulo square of this component. This is the probability to have the eigenvalue, lambda I, as an outcome of the measurement. Another way to see it is the following. If we represent the state in the basis given by the eigenvectors phi I, then the probability to have the eigenvalue, lambda I, as an outcome of the measurement, is the modulus square of the amplitude Ci of the component of the state with respect to the phi I basis vector. And the projector operators do exactly this job, since they project the state in the eigenvector basis, which is the way we evaluated the representation of a state when we change basis. This is known as the Born rule. Born was the first to insist that the wave function has to be interpreted as a wave of probability. In the Copenhagen interpretation, no other physical meaning had to be given to it. For example, the spin along the z-axis of a 1/2 spin particle is the observable associated to the Sz matrix, which is proportional to the Pauli sigma z matrix, and which eigenvectors are the up and down states. If we have a particle in the up state, which is represented with respect to the eigenvectors of sigma z with coefficients 1 and 0, then a measurement of the spin along z will give, up with probability 1, and down with probability 0. But, if we have a particle in the state right, which is represented with respect to the eigenvectors of sigma z with coefficients both equal to 1 over square root of 2, then a measurement of the spin along z will give, up with probability 1/2, and down with probability 1/2. Another example is the particle in one-dimensional space. For the position operator x hat, clearly any real number x0 is an eigenvalue and the relevant eigenvector is a Dirac delta function centered in x0. This because x times a delta centered in x0 is equal to x0 times the same delta. This means that the wave function is really a wave of probability, because its amplitude square in x0, which is the projection of the function on the basis of the deltas, is proportional to the probability to find the particle in that place when we measure it. For the momentum operator, clearly any real number p0 is an eigenvalue and the relevant eigenvector is an exponential function which represent a particle of definite momentum, and completely unknown position. This can be seen easily applying the operator to the exponential function. Axiom 4. After a measurement of an observable A giving as an outcome the eigenvalue lambda I of A, the state of the system will change to the relevant eigenvector phi I. Let's see what it means. Suppose we have a 1/2 spin particle in a given state. And suppose we measure the spin along z and we find 1/2, which is the eigenvalue relevant to the eigenvector up. Then, after the measurement the state of the system will be up. Same for the particle in one-dimensional space. If we measure the particle in a position x0, after the measurement the state of the particle will be a delta centered in x0. We say that after the measurement the state of the system collapses in the relevant eigenvector. In other words, before the measurement, the state of the system is generally in a superposition of the eigenvectors of A. However, when we measure the observable relevant to A, this action destroys the superposition, and only one of the eigenvectors can survive. The collapse of the wave function is probably the most important concept of the Copenhagen interpretation. Since a measurement will change the state of a system, not all observables can be measured simultaneously. The relevant observable are called incompatible. From a mathematical point of view, this is due to the fact that the order operators act on the space matters, and it can be expressed by an operation called commutator. For example, we cannot measure the spin along different axes because their operators do not commute. If we apply the commutator to them, we get a non-zero result. The same is true for the position and momentum operator. This is another way to express the uncertainty principle. However, for a particle in three-dimensional space, we can measure quantities relevant to different axes simultaneously because their operators commute. Two operators are incompatible when they do not have a complete set of common eigenfunctions. Note that for axiom 3 and 4, to keep the description simple, we have always assumed that there is a one-to-one map between eigenvalues and eigenvectors. For some operators, it may be possible to associate multiple or even infinite eigenvectors to a single eigenvalue. The relevant eigenstate is therefore a subspace of the state space. Axiom 5. The wave function evolves according to the Schrödinger equation. Let's see what it means. The wave function evolves according to a partial differential equation called the Schrödinger equation. It comes in two forms, the time-dependent and the time-independent Schrödinger equation. In these equations, the operator h hat is called the Hamiltonian operator and it's the operator associated with the observable energy of the system. The first form is used when the Hamiltonian is time-dependent. The second form is less general, and it can be used only when the Hamiltonian is time-independent. Let's see how to derive the time-independent Schrödinger equation from the time-dependent. If we solve the equation by separation of variables, psi can be expressed as the product of a function of space and a function of time. It can be proved that the function of time is just an exponential and it depends by a parameter e. By substituting psi in the Schrödinger equation, the term depending on time go away. And we are left with an equation depending only on x. This is the time-independent Schrödinger equation. The solutions of this equation are called stationary states and there is one solution for every energy level of the system En. We get the final solution adding the time-dependent part. Let's see an example. In classical physics, the Hamiltonian of the harmonic oscillator is the sum of the kinetic and potential energy. It is a system which has a potential going as x square. A quantum equivalent is a particle in a well which potential goes like x square. We can find the quantum Hamiltonian just promoting space and momentum of the classical Hamiltonian to their equivalent operators. In this case p square become just a second derivative operator because the square on an operator means the operator applied twice. We get eventually the time-independent equation which gives the stationary state of the quantum harmonic oscillator. We will not solve the equation of the harmonic oscillator, which is one of the most important equations in quantum physics. However, in this picture, you can see what the various stationary states look like and their relevant energy levels. This concludes the axioms of quantum mechanics. However, before I finish, I want to show how the axioms lead to the concept of entanglement. A common example of an entangled state is given by the singlet state of two 1/2 spin particle that may be placed far each other at will. We know now how to evaluate the up-down state and the down-up state. They are the tensor product of the states of the two particles. The singlet state is simply a superposition of these two states. Now we may want to decompose this state in order to find the state of each particle. However, this decomposition does not exist. The tensor product and the superposition of states give us a state of the composite system that cannot be factorized. By acting on a part of the system we will inevitably have an effect also in the part which is far away. And, this what the entanglement is about. Thanks for watching.